Today, I'll introduce a topic involving two examples about the integral function. Using these two examples proof, including the application of the property of the uniform continuity. Firstly, let's look at the first question, which is in the book of mathematical analysis written by Apostol, which is an interesting book involving a lot of good examples for my learning journey of mathematical analysis to understand some problems better. Since my teacher tells me that theorems come, theorems go, but only examples lies forever. Now let's see this problem. When we see that, we just maybe we don't know how to handle it, but when we write down the step by step, we could know this guy, and we have two important property. One is that Fn is a continuous function defined on this composite, and also the second is that it's uniformly convergent to f on this composite. I don't know if this relationship is true. Since we have this limit and this integral, and Fn is uniformly convergent, we have the property that the uniform convergence preserves integrability, so we could interchange the limit and the integral, so we could write so we want to know, is this equal to this guy? So we make a change of this. We just want to know, is this true? So if we want to show it is equal to 0, we may use the squeeze theorem. So we want to find is an upper bound and a lower bound of fx to know is this go to 0 and go to infinity. So we haven't used the property of this, which is Fn is continuous function defined on 0 to 1. So Fn is continuous so we know that since F converges to F uniformly, we know by the uniform convergence preserve continuity, we know that F is continuous on this compact interval. Actually, this is a theorem that with an easy proof. If we draw this picture of this proof, now uniform convergence preserves continuity. The condition of this is Fn uniform converges to F, and the Fn is continuous. Want to show F is continuous, and this means to show this, we need to show if And this tells us that when it's big enough, this tells us that so let's draw this picture. If we want to show prove is less than epsilon or a constant times epsilon, and we have epsilon. So this is by uniform convergence. This is by continuity, and this is also by so we know this. It's actually a realization of triangle inequality like that. So we just write so we finish our proof. So let's continue. Here we know that f is continuous on the convex side, so we know that f is uniformly continuous. So we know that so we could take epsilon to be 1. So we know that here fx is bounded by f like that, and in this question this distance is 1 over n. And we take fx0 to be f1 in this question, which means we want to use the definition of uniform continuous. We have for so we know that actually it's a constant that's not relevant to any indeterminate thing. So we know that we want to know if this really exists. Since we have that n could be bigger enough, since we have let n goes to infinity, and by the Archimedean, there always exists n such that is bigger than 1 over n. This means that this 1 minus 1 over n is in the neighborhood of the delta neighborhood of 1. So we have met this condition, so we have this. So in this here we could just write this f1 plus 1, this is f1 minus 1. So we have this goes to 0 as n goes to infinity. So we finish our proof. So what we write here? So this is true. So we have proved this.